We're actually going to record the video, and you can watch it later.
Follow my blog, Foxy.
Shout outs in the beginning. Oh my. I should wear those glasses. Absolutely.
Just don't break them, don't hold sisters.
Pressure.
Pressure.
It matches your outfit.
It kind of does. Wait, upside down? Which one?
Even better. It doesn't matter.
It doesn't, huh? Alright, guys. Here we go. I don't know where I was going with that voice. Here we go. Understanding with the G. Independent events. Okay, so we have independent versus dependent events. It's kind of hard to see you guys. I never talked with glasses.
Put it back on.
How about that?
That's not the real.
No, it's not. It's just throwing me off my game. I need eye contact. Yeah. Here we go. This is old. We've already done this. This is what we've seen so far. Independent events. One event has no effect on the next event. So if I have my coin here, Susan B. Anthony coin, or flip it, heads. Does it matter that I just got a heads for my next flip?
No.
Does the next flip, is it dependent at all that I just got a heads?
No.
No. I can get anything right here, right? Heads or tails. Well, anything. Let me see. Heads. Those two events are not connected. They're independent. That makes sense, right? Okay. It's actually really important to be able to see the difference because, like we were saying, the probability of events in your life, you want to be able to see what's independent and dependent. Because a lot of times we're making assumptions. We think one thing's connected to another, and that's how we make illogical decisions sometimes. All right. Throw in one die. If I throw one die, how many options do I have? My sample set is 1, 2, 3, 4, 5, 6, right? So I roll this. I roll it right here. I got a 6. What was my chance of getting the 6?
1 in 6.
1 in 6. The options desired, one of them. The total options, the sample set is on the bottom, 6. So 1 out of 6. So these are independent events. This is old. This is what we've already done. And what we're going to do is we're going to have over on the right side one formula we use to test if it is an independent event. So this is the new thing here. I didn't write that. This is new. Okay. New. Because now we're talking about dependent events. Look at this. The outcome of one event affects the next event. So if I draw a card and I discard it and I pull another card, what's going to happen? Let's see. I pull a card. I already shuffled it 7 times, just imagine. Pull a card. What do we have?
Ace.
We have an ace. I put that card down. So the ace of spades, there's one option. And how many cards in the deck from the beginning here is 52, right? 52. Now I take that ace, I put it down, I discarded it. Now, what is the chance of, say, me getting a king of spades? 1 in?
51.
51.
Why is it 51?
Because you're drawing one card.
Right?
You're taking out one card.
I discarded one card, so the event is dependent because now I have fewer options to pull from. Now I have 1 in 51. So the chances get, they get better as you get rid of more cards, but they're actually dependent events. We have to see that as they're dependent events. So draw a card, discard 1. Is it logical where you can see those differences? You can see those differences? Maybe not yet. So we're going to do this example problem, and I want you just to watch with this. Don't worry about writing it down, because we're going to have options later. The experiment is pick a ball without replacing it. That's it. So here are all of our options, and I'm going to put them in this bag, and I'm going to ask somebody to pick it. So how many pinks?
2.
2. You see the diagram here? 2 pinks. How many oranges?
3.
3. Oh, I just made it into a nectarine. All right, how many greens?
1.
How many yellows?
1.
All right. So, probability of you pick a green ball. What?
You want to pick it together?
Good. You want to pick it together?
Yeah.
That's going to be interesting. I'm looking forward to it. What is the probability of picking a green ball on my first draw?
1 out of 1.
Green. 1 out of 1, 2, 3, 4, 5, 6, 7. To pick a green ball, the probability is 1 out of 7. Now, to pick a yellow ball, and we're going to pick a ball without replacing it. So let's say that I just picked out a green ball. I don't replace it, I put it here, and I'm going to go over here. And there's going to be 3 hands grabbing one ball somehow. They don't even get there.
All right.
Got one?
Who got it? Who got it? Who got it? Who got the ball? Ready? Together? We all got it.
That's the first time that's ever happened anywhere, ever.
Awesome. History.
We just had three hands picking one ball, and we got pink. All right, so now we picked the pink ball, but before that happened, what were the odds? What was the probability of getting a yellow ball? I want you to figure that out. I had already taken a green out, so what was the chance of getting a yellow?
1 out of 6.
1 out of 6. 1 out of 6. Okay. If this, instead of being yellow, if it wasn't yellow and it was pink, what would have been the chance of getting a pink? 2 out of 6. Because I took out the green one already, now the probability for the next pull changes. You see how that is a dependent event. It's dependent because the first event that happened is going to affect the probability of the next event. You see how that works? Okay. So if I pulled out, let's say the next one I did was, I pulled out 2 additional balls there. So now we have, let's see, we have 2 oranges gone, we have a green and a pink gone. So what is my chance of picking a orange ball now?
1 out of 3.
1 out of 3. So is that pretty good odds?
Yeah.
That's pretty good odds? Well, it's equal odds, right? Because all the other left. It's 1 and 3, 1 and 3, 1 and 3. Who's lucky? I know I'm lucky. Anyone else know who's lucky? Alejandro. All right, feeling lucky? All right, let's go ahead and pick a, what did I say? Orange ball? Orange.
Easy. No peeking.
He's not gonna get it. He's by himself.
Alejandro is lucky. He had a 1 in 3 chance, and he got the orange ball. Okay. So, but you see how if you, so Alejandro, if you were, if it was pick an orange ball or do 500 push-ups, would you put your arms at risk to do a 1 in 3 chance?
What would I win?
You would win
Not having
an entire bag of Starburst.
Then yeah, do it.
You win $1.
I'll still do it too.
Still do it.
That's 100 pennies.
Okay.
That's a lot of
True.
pennies.
You can do all the coin flipping experiments.
Yeah.
That's right.
Gotta use them.
All right. So what I'm trying to point out, if you have a 1 in 3 chance of anything happening, like a life event happening, something happening, that isn't very high probability. So you may be more cautious with taking that risk. Okay. That's kind of the main thing I want to point out. So. What's that?
Life lessons from history.
Life lessons through math. Oh, wait till next week. I have the most important logic, choice making thing.
Nah.
Yeah.
It's better than that.
I'm great. Wait a minute. Walk out.
I got to teach you.
Oh, I lost my pen.
It really dropped. You had a pin drop that disappeared. I think it's a good sign. All right, so let's look at what we had already. The probability of A, again, until the red line here, just kind of follow with me. The probability of A, which is picking a green ball, is 1 in 7. The probability of B was to pick a yellow ball. We had 1 in 6. Is there anything that overlapped there? Is there anything that overlapped? I wanted to pick a green ball, and I wanted to pick a yellow ball. Yes?
Why is pink ball? Oh, pick the yellow ball. Never mind. Sorry. That's a pink ball.
Got it? There were 2 pinks, right? 2 pinks and a green. Because we took out 1 ball, it became 1 in 6. Are any green balls also yellow balls? Does that even make sense? Are there any green balls that are also yellow balls? No. So the probability of, if there's an intersection between the A and the B, the thing in common, right, where the streets overlap, it's 0 out of 7. So we're going to go and look at this because we can only test if it's an independent event using this kind of algebra part. I think logically you can figure all this stuff out on your own, but now I want you to go ahead and in a box, really important, let's put the independence test, the independent event test. If it's true, it's independent. And that's how we're going to be able to figure these out pretty quick. Okay. And then we'll do, it looks like we're going to get to do the page 37 task, and then we'll do the other part on Monday. Just this part. Okay. Need you guys to have that boxed out. Nice and clean, nice and neat. Okay. Pretty quick, give you a couple more moments there. Definitely square it out. Once you put stars around that one, that one's super important. Okay. Final moment. Hungry?
Yeah.
Did you eat this morning?
No.
Yeah,
I haven't eaten since yesterday at 3 o'clock. I had a Whopper.
One of these?
Jordan.
Hmm?
Oh, that one.
Okay. Sorry, I only had one. Oh, friend share.
Thank you.
You're welcome. All right, here we go. If it's independent, then we put it into this equation. What's this dot mean again? For those that maybe remember.
Multiply.
Multiply. We're going to multiply the two probabilities together. That's pretty good, huh?
Okay.
I like them. They're like cookies. All right. If it's true, then it is an independent event. So we're going to see if this is independent. Let's see. What did we get for the probability of A intersecting with B? Was there anything that intersected between being a yellow ball and a green ball? It's 0, right? There's nothing. So we worked these out before. All you have to do now is take that probability of getting a green ball, the probability of getting a yellow ball after you take out one ball there. And then what was the union? Are there any in common? It's 0. Yes. All right, so let's put in the rest. Probability of A is 1 out of 7. Probability of B is 1 out of 6. When we have fractions, yeah.
Why are we doing the probability of yellow with the green ball out? Why aren't we doing it just like with the green ball in?
Got it. Because the experiment, which tells us what we're going to be doing, the actual action, not what we're looking for, but what's going to happen, is we pick a ball without replacing it. So after we picked the green ball, we left it out. Therefore, the probability of getting a yellow ball is 1 out of 6 instead of 1 out of 7.
Okay.
Right? Got it. All right. When you're seeing if it's independent, you multiply the fractions. When you're multiplying fractions, you multiply straight across. It's not adding where you need a common denominator. So if I multiply straight across, I get 1/42. And is 0 over 7 equal to 1/42? No. It's not right? This is wrong. This is false. So because it's false and I was testing if it's independent, I know that it's dependent. And then let's think about that. Does that make sense? I took out one ball. The probability will change because there's one less. Instead of 1 out of 7, now it becomes 1 out of 6. All right. So this is the main thing we're going to do right here. This is probably the hardest thing to figure out. I think that probability of one thing or the other with our experiment, we can figure that out. But really what this is asking is what's the probability of drawing a green ball and a yellow ball at the same time? And that was just 0. You can't have that. It's impossible. So that is our first experiment together. We're going to do this one as a large group here. So go ahead and get out your workbook. Turn to page 37. If you don't have your workbook, then you got to take notes somehow where you can turn this in. Okay, we'll do this, and then that's probably going to be the day. But maybe we'll have a shout-out at the end if anyone has shout-outs. Shout out to all my Irish family members.
Yeah, shout out to Brazil.
Brazilian.
Yeah.
I gotta learn how to say hello in Brazilian.
Como tá o Ibu?
Como tá, Lu? They're all.
Oh no, are you done that?
That's fresh.
That's the only thing I saw you in French, and now you can't stop using it.
No, but that's all.
Yeah. Yeah, I was about to say.
Get this over here. 37? Yeah. All right, here we go. We're not done. Workbooks out. Workbooks out. Find your seats. Here we go. Here we go. The experiment is flip a coin 2 times. Again, if I flip one coin, does it matter? I just got a heads. Does it matter that I got a heads for my next coin flip? Does it matter? I just got a heads. It's a whole new situation, right? Second time, I got tails. Okay. So what I want you to do is first, I'm going to erase these and start over. Let's make 2 diagrams. Say I roll a heads first. That's my first time, right? What are my 2 options that I can have for my second flip, heads or tails? So I could do a heads first, and then I could have a heads or a tails. So this is like the first flip. This is the second flip. So if I roll I flip a tails. What is the option for my second? Heads and tails still, right? Okay, heads and tails. So the first experiment, we're only flipping the coin twice. What is my sample space as far as combinations that I could get between my first flip and my second flip? So watch this. My sample space, if I'm flipping it twice, I could get a heads and a heads. Everyone see that? Heads, heads. I could get a heads first and then a tails second. Right? I could get a tails first and a heads second. Or I could get what? Tails, tails. Does everybody see how I got these 4 outcome options? This is my sample space. Sample space is everything that's possible. If I'm flipping twice, here are the only combinations I can get. Heads, 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 tails, tails, heads, and tails, tails. And using this kind of tree, it helps me see the paths. Yeah, heads, heads, tails, tails, heads, tails, tails. Those are the only options you can have. Okay. So let's see what we have here. The outcomes. Outcome A is heads on the first toss. What is the probability of A? To get a heads on the first toss, how many options had a head in the first toss? How many?
1, 2, 3.
Heads, heads.
3.
Heads, tails. Those have heads in the first flip.
Oh, the first flip.
Yeah.
Oh, okay.
First toss. First toss. So how many options do we have?
2 out of 4.
2 out of 4. 1/2. How about the probability of B? If we have B, it's heads on the second toss. Huh? How many have heads on the second toss?
1.
1,
2.
2. So it's 2 out of 4. It's 1/2 as well. Okay. You see, you go and you see what the experiment's having. You make some sort of diagram that shows you those options. You put your sample space. These are all the possible options. And then you're just looking at each of these outcomes and seeing what's the probability. All right, how about the probability of C? Exactly 1 heads. How many options have only 1 heads?
1.
1,
2.
2. 2. Exactly 1 heads. So again, we have 2, so we have 1/2. See if the following is true. Let's see. Is there any intersection between A and B? Let's look at them. Heads the first toss, heads the second toss. Are there any situations where it's heads the first toss and heads the second toss? How many? Let's see. Heads the first toss, heads the second toss. That's the only one that works out like that. So this is 1 out of 4. What was the probability of A? Found that 1/2 times 1/2. We multiply straight across. We get 1/4. Do these match? Those match, right? Those are equal, so we know that it's true. Therefore, it's an independent event. That's our answer. Let's look to see what we did again. We have all the different options for flipping twice. Heads, the next option would be heads or tails. Tails we get could be heads or tails. We wrote out all the sample options. Heads, 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 tails, tails, heads, tails, tails. Then we just go over here and see how many desired outcomes over the total possible outcomes. So the probability of just the heads first is 1/2. Heads second is 1/2. Exactly 1 heads is also 1/2. The independence test is what we're using for all of this. So let's see if the next one works. It's easy. Is there any intersection between A and C? Let's see. Get exactly 1 heads. And A is heads on the first toss. Is there anything in common between those where both of those conditions happen? Okay. When does that happen? Get exactly 1 heads, that would be either this one or this one. So these are for, this is C options. Heads on the first toss, which one of these has heads on the first toss? Heads, then tails, right? Yeah. So this is the only one that satisfies the intersection of A and B, where both of these are true. It's 1 out of 4. We know the probability of A is 1/2. Probability of C, 1/2. We multiply that, we get 1/4. And are these the same? Same?
Yeah.
With confidence?
Yeah. Yeah.
All right, so it's true, it's independent. I think actually this lesson helps with all the other lessons because we're just finding the probability. It's kind of like this is all built to them. All right, we have just a couple minutes. Let's do this quick. Are there any options that are in common, that intersect between our B and our C? Let's see. Heads on the second toss? Exactly 1 heads.
Yes.
Yes.
Yep.
How many? Heads on the second toss? Which one's that? Heads on the second toss. That's those. And then get exactly 1 heads.
Yep.
This one, right?
Yeah.
All right, so we have this option that work. So we have 1 and 4 is equal to, since all these are half, I know it's half times half. 1/4. Do these match? It's true. We have an independent event. You see how this works now? You kind of have to depend on it.
After you went into the outcomes and showed like
How these all
heads
work.
on the second toss and all that. Yeah,
It helps.
makes
Okay.
sense.
Okay, great. Let's do this last one. Are there any intersections between A, B, and C? Let's erase it. We'll kind of mark. So we have heads, heads. We have heads, tails. Tails, heads. Tails, tails. All right, let's see. Let's do A first. A is heads the first toss. This is an A, that's an A, that's all. B, heads the second toss. This is the B, this is the B. C, get exactly 1 heads. Exactly 1 heads, C. Exactly 1 heads, C. All right.
No.
Are there any options where we have both A, B, and C work out for one of our options here?
No.
This is A and B, that's A and C, and this is B and C. So there's nothing that actually satisfies an intersection of all of them. So how many options do I have out of my 4?
0.
Very good.
5.
And then the probabilities were 1/2 times 1/2 times 1/2. Okay. We multiply all that, we get 1/8. Is 1/8 the same as 0/4?
No.
No. So it's false. What kind of event? True was independent event, so it's
Dependent.
false. Dependent event. Yeah, I think together this lesson might actually answer some of the other questions. They can see that. Yeah, they can see that. All right, that brought us to the end. We're going to actually pick this up on Monday. We'll work on this on Monday for probably about 15 minutes for the next part. If you want to get ahead of the game, you can do the second experiment on that page. But take a picture of this. Take a picture of this. All right, any shout-outs today?
Box Potatoes 2. Follow us. The blog.
Oh, you shout out your own? Oh, man. No shout-outs? We're good, it's Friday? Oh, Jordan, you're in the video.
I want to get in it.
No, you can't. Oh, yeah, that's where it is. That's right there.
I know it's right there, Mr. P. I'm not silly.
Not silly. All right, how about shout out to N.A. from his image? It didn't show you guys' face. I do a shout out to my sister. It's her birthday Monday. I do a shout out to the 12% of me that's Irish for
Shout out to my dog.
St. Patrick's Day. So I'll give you a 12% shout out. It's, I don't know words I gotta say.
We have to make sure when it's our birthdays, we have to give our shout outs.
That's right.
Exactly.
Any birthdays? Anyone's birthday?
My birthday's in January.
A retro shout out to all the birthdays I missed. How about that? All right.